Let's see. Okay, so we're talking about viscosity of solids and liquids. And the criterion of phase equilibrium, which we'll derive later, is that when two phases of a substance are in thermodynamic equilibrium, the molar free energies are equal in both phases. So if it is liquid and vapor in equilibrium, that means if water is in equilibrium with its vapor, then the molar free energy of a component of water in the liquid is equal to molar free energy of water in the vapor. Okay, so that's the condition which we'll derive later. So every solid or liquid has some vapor pressure when they are in equilibrium. Solid vapor equilibrium is essentially sublimation, when, for example, naphthalene goes from solid phase directly to vapor phase, or dry ice, which is CO2 in the solid phase, goes directly to vapor phase. Okay. So every solid or liquid has a definite vapor pressure. So water has a vapor pressure above it. Similarly, dry ice has some vapor pressure, CO2 has some vapor pressure above it. So at this pressure, the solid or vapor or liquid is in equilibrium with its vapor. So water and water vapor are in equilibrium. When we say equilibrium, what do we mean? Can somebody talk about equilibrium? What does it mean? इक्विलिब्रियम नहीं पता आप लोगों को?
सर इक्विलिब्रियम पता है कि इट इज द पैरामीटर इज कांस्टेंट विद रिस्पेक्ट टू टाइम, लेकिन यहाँ पे वो क्या मीनिंग है वो नहीं समझ में आ रहा.
Okay. Let's see.
सर इज इट दैट कि अगर हमने कोई पैरामीटर चेंज किया, अगर प्रेशर चेंज किया, तो उस कंडीशन के ऊपर उसका कोई असर नहीं दिखता.
Okay. So let's see what is equilibrium. What is this thing? Any guesses? क्रूड है ये, लेकिन क्या है? समझ में आ रहा है?
Sir, not visible.
नहीं दिख रहा किसी को?
No, sir.
नहीं.
किसी को नहीं दिख रहा कि किसी किसी को दिख रहा है?
300 आए सर, दिख रहा है.
दिख रहा है ना? दिख रहा है सबको अभी?
यस सर.
No, sir.
How many people can't see? Raise your hands. How many people can't see? Raise your hands.
सर पेंट में दिखाइए ना.
अरे पेंट बहुत डिफिकल्ट होता है, व्हाइट बोर्ड बहुत कॉमन रहता है. What is this? Any guesses?
300.
Seesaw.
जिसने पहले देख लिया था उसको पता है, राइट? तो दिस इज सीसॉ. सीसॉ में क्या होता है? देयर आर टू पीपल एट द अदर टू एंड्स ऑफ अ सीसॉ. जिसका वेट ज़्यादा रहेगा और ज़्यादा प्रेशर लगाएगा. सपोज दिस पर्सन इज पुटिंग लॉट ऑफ प्रेशर हियर, राइट? तो क्या होता है? नीचे जाता है, दिस गोज अप. सो इज दिस इक्विलिब्रियम? ऊपर नीचे होता रहेगा, राइट? ये प्रेशर डालेगा, ये नीचे हो जाएगा. इक्विलिब्रियम इज व्हेन both are here. This is equilibrium. So equilibrium is when there is net. पहले हमने देखा था, I think somewhere you have seen net force acting on a system is negative, right? कहीं तो देखा था हमने, याद आ रहा है? नहीं आ रहा. So basically what we are saying is, याद आ रहा है कुछ?
हाँ सर.
Right? So here we are saying is कि in this case the net force acting on this seesaw or this system is zero. ये इसका जो प्रेशर है और इसका जो प्रेशर इंक्लूडिंग वेट इज सेम. सो इस बैलेंस में है, राइट? ना ये ऊपर जाएगा ना नीचे आएगा. सो व्हेन यू से वाटर एंड वाटर वेपर आज निकले, दैट मीन्स जो वाटर वेपर है न वो लिक्विड में ट्रांसफर हो रहा है, न लिक्विड है वो वाटर वेपर में ट्रांसफर हो रहा है. सो नेट ट्रांसफर और मास ट्रांसफर बिटवीन लिक्विड एंड वेपर इज जीरो. दैट इज इक्विलिब्रियम. ट्रांसफर कब तक होता रहेगा? जब तक इक्विलिब्रियम होगा. इक्विलिब्रियम हो गया उसके बाद मास ट्रांसफर नहीं होगा, राइट? सो व्हेन वी से इक्विलिब्रियम है बिटवीन लिक्विड एंड वेपर, दैट मीन्स देयर इज नो मास ट्रांसफर बिटवीन लिक्विड एंड वेपर. जितना है उतना ही रहेगा. एंड दैट इज द मैक्सिमम व्हिच कैन बी ट्रांसफर्ड फ्रॉम लिक्विड टू वेपर. There's the limit of mass transfer between liquid and vapor. Similarly for solid and vapor, yeah.
सर वो मींस ट्रांसफर होते रहता है ना, बट डिफरेंस द नेट ट्रांसफर इज जीरो.
Net transfer is zero, ना? What? It's net
मतलब
transfer. Yeah, बोलो.
मतलब जितना लिक्विड वेपर में ट्रांसफर हो रहा है उतना ही वेपर लिक्विड में ट्रांसफर होता है.
So net transfer is zero, ना? That's what I mean. When there is no transfer, that means there is no effect. You can't see the effect, right? जो हो रहा है वो, that is mechanism. What you see is no effect. You don't see any change in vapor composition. You don't see any change in liquid composition. Right? अगर ट्रांसफर होगा, नेट ट्रांसफर होगा तो कंपोजिशन चेंज होगा वेपर का, राइट? बट सिंस देयर इज नो नेट ट्रांसफर, देयर इज नो चेंज इन द कंपोजिशन ऑफ द वेपर. Although mechanism, whatever mechanism is the underlying mechanism, it may be there. थोड़ा उधर से ऊपर आ रहा, लिक्विड से वेपर जा रहा है, वेपर से लिक्विड आ रहा है, बट नेट ट्रांसफर इज जीरो, राइट? Is it okay?
यस सर.
Okay. So now what we are saying is बैलेंस हो गया दोनों के बीच में. यहाँ पर इसके ये प्रेशर लगा रही है, प्रेशर लगा रहा है, बट बैलेंस होने की वजह से इट इज इन इक्विलिब्रियम. Similarly, when we talk about liquid and vapor, they are in equilibrium. That means the net transfer is zero. Something may be transferred from liquid to vapor, vapor to liquid, but net transfer is zero. Similarly for solid and vapor. Okay. So let's come back to our PDF. So in this case, the condition for equilibrium is that just a minute. Okay. So we have said that condition is that molar free energy in the liquid phase is equal to molar free energy in the vapor phase for that component. We are talking about pure here, pure liquid and pure vapor. So molar free energy of water in the liquid phase is equal to molar free energy of the water in the vapor phase for liquid vapor equilibrium. Similarly, for solid vapor equilibrium, molar free energy in the solid phase is equal to molar free energy in the vapor phase. Then there is equilibrium between solid and vapor in this case, and liquid and vapor in vapor-liquid equilibrium. And we have seen that G is equal to RT ln F plus C. If you put for liquid and vapor phase, you get RT ln FL plus C is equal to RT ln FV plus C. And CC cancels out, RT cancels out. What you get is viscosity in the liquid phase is equal to viscosity in the vapor phase. That is the condition for liquid vapor equilibrium. And similarly, viscosity in the solid phase is equal to viscosity in the vapor phase for solid vapor equilibrium. So this is what we derived from molar of free energy. That means viscosity of the solid or liquid is equal to viscosity of vapor in equilibrium, provided reference state is same. And we always select the same reference state for both. Okay. So if the vapor pressure is not very high, we have seen that, right? Fv is equal to viscosity for the vapor phase or gas phase is equal to vapor pressure. And for vapor equilibrium, what will become is Fv, that's viscosity in the vapor phase, equal to viscosity in the liquid phase equal to vapor pressure. And similarly for solid vapor, viscosity in solid phase equal to viscosity in vapor phase equal to vapor pressure. So this is a solid vapor and liquid vapor equilibrium condition. Okay. Any questions so far?
सर वो रेफरेंस स्टेट क्या होता है?
अरे कितना समझाया रे लास्ट वीक? रेफरेंस स्टेट नहीं बताया था लास्ट वीक? Who was that?
सर देवेंद्र.
देवेंद्र बताया था लास्ट वीक रेफरेंस स्टेट क्या होता है? भूल गया क्या? To define viscosity, because viscosity is not easy to define, right? So when you say F by P is equal to 1, right? At low pressure. So what is the reference state? Ideal gas at low pressure, right? It's always relative. Because viscosity is not measurable, you have to always define with reference to something. बताया था ना temperature कैसे define करते हैं हम 0 and 100. That is the reference state. Similarly, we define viscosity as viscosity equal to pressure at low pressure. That is the reference state. याद आ रहा है कुछ?
हाँ सर वो याद है पर यहाँ पे क्या है वो नहीं समझे.
Same आएगा ना. See, whatever you define reference state for the liquid phase, that same thing has to be used for solid phase. That's what it means. Reference state जो भी हम define करेंगे ना, it is going to be same. Generally क्या होता है? We define the reference state as same temperature and same pressure. Same temperature, same pressure for the liquid phase as well as for solid phase. Then only we can say it is same. Because ultimately हम measure वही करते हैं, temperature, pressure ही measure करते हैं, right? So we always say जैसे अभी low pressure define किया हमने गैस के लिए, वैसे solid liquid के भी define करेंगे. You use the same reference state for both liquid viscosity as well as for vapor viscosity. You cannot have a different reference state for liquid and different reference state for vapor. That's what it means. Because viscosity is always related to a reference state. When we say 25 degrees centigrade, what does it mean? It is related to 0 degrees centigrade. इतना ज़्यादा है. Right? So if I change the reference state of 0 degrees centigrade, suppose I say reference state is now 10 degrees centigrade, then what is the temperature? It will change. It is 15 degrees centigrade. Actual temperature. समझे क्या, देवेंद्र?
नहीं समझा सर.
Suppose I have defined 0 degree centigrade as reference state, right? Arbitrary है ये. They said it is 0 degree centigrade. Now suppose I say ice का melting point is 10 degree centigrade. I defined that arbitrarily 10 degree centigrade. तो डिफरेंस कितना होगा एक्चुअल टेम्परेचर इसमें?
10 का ही होगा.
15 का होगा ना. अगर 25 डिग्री सेंटीग्रेड टेम्परेचर है 0 के रेफरेंस में और मैंने बेस चेंज कर दिया 10 डिग्रीज कर दिया तो क्या हो जाएगा डिफरेंस रिलेटिवली? नहीं समझा क्वेश्चन मेरा?
नहीं.
Suppose the actual temperature is 25 degrees centigrade and my base is 0 degrees centigrade, right? Reference temperature. Suppose I change the reference temperature from 0 degrees centigrade to 10 degrees centigrade. So relative to 10 degrees centigrade कितना होगा temperature difference?
15.
15 होगा ना? So that is what we are talking about. Fugacity is always related to something, some reference state. If I change the reference state, fugacity will change. जैसे मैं टेम्परेचर रेफरेंस स्टेट चेंज कर दिया, 0 जगह पर 10 कर दिया, 5 कर दिया, तो मेरा डिफरेंस विल चेंज ना, एक्चुअल टेम्परेचर कैसे चेंज हो रहा है. So similarly, fugacity is always related to a reference state, which is always defined as for ideal gas at low pressure. If I change something else, if I change, say, if I say that fugacity reference state is now ideal gas at 5 atmospheres, then the fugacity reference will change, fugacity value will change because reference has changed. That's what we are saying कि reference has to be same for whether liquid है, vapor है, solid है कि vapor है. Reference should be same. समझा क्या?
Yes, sir. Absolutely.
Okay. So if vapor pressure is very high, we have taken very low pressure, right, as a reference state. So suppose vapor pressure is very high, and vapor cannot be treated as ideal gas because we said only at low pressure we can treat as ideal gas, right? That's the reference state. But if the vapor pressure is very high, then we cannot take it as a ideal gas, and then we use this equation, approximate method, जो हमने देखा था ना, last week derive किया था method for fugacity, V into P by R, P square by RT. So that then we use this method for high pressure. So fugacity at saturation, that means vapor at vapor liquid equilibrium, is equal to volume into saturation pressure, that is vapor pressure whole square divided by RT. Approximate method जो हम last week used, then we use this method at high pressure. Okay. Where Psat is equal to saturation pressure, that means vapor pressure of the vapor or gas, and Fsat is saturation fugacity at saturation. And we know that equilibrium condition is Fsat is equal to Fl or Fv is equal to Fl. So what, and for solid vapor it is saturation fugacity is equal to F solid, vapor liquid and solid vapor के लिए, ठीक है. And we also know that RT dlnf is equal to VdP, ये हमने derive किया था पहले, ठीक है. So what we get is dlnf is equal to V by RT dP, and we know that liquid can be considered as incompressible, pressure का effect नहीं होता liquid पर, so V can be taken as constant for liquid. What we get is dlnf, V can be taken out of integral into integral dP from saturation pressure to actual pressure, and this limit will be saturation fugacity to actual fugacity. तो क्या मिल जाएगा हमारे को? What we get is ln f by f sat is equal to V by RT P minus P saturation. ठीक है. सिंपल डेरिवेशन है, ज़्यादा कुछ नहीं है इसमें. वी जस्ट स्टार्टिंग फ्रॉम हियर एंड इंटीग्रेटिंग इट between saturation pressure and actual pressure, and saturation fugacity and actual fugacity. And where V is the molar volume of liquid, we are taking it out of the integral because it is constant for liquids. ठीक है. So this is how we define fugacity for liquid or vapor. So if you know saturation fugacity, you can find out actual fugacity. What we need is vapor pressure, actual pressure, and we can find out this fugacity of the vapor or the liquid, because it's equal for both. ठीक है. So this is case of solid vapor and liquid vapor fugacities. Any questions? ठीक है, there is
Sir?
no question. Yeah.
सर वो लास्ट वाला जो एक्सप्रेशन है ना ln f by f saturation, उसमें f l है क्या?
See, it will depend. What do you want to find out? Do you want to find out solid vapor? See, ultimately हमने क्या derive किया? Equilibrium पर FL is equal to FV, right? So I can calculate
Yes,
anything.
sir.
They are equal, right? So if I want to calculate FL or FE, where they are equal, right? All I need is saturation or vapor pressure में equilibrium में क्या है fugacity और P set कितना है. So I can find out this F. This is applicable for both solid vapor and liquid vapor, both. और अगर सॉलिड रहेगा
सर
तो सॉलिड का वॉल्यूम भी कम. या
सर एफ एल इक्वल टू एफ सैचुरेशन होता है ना?
नहीं, FL इज इक्वल टू FV होता है, सैचुरेशन नहीं होता है.
नहीं होता है.
राइट, वी हैव सीन दिस, राइट. ये था F saturation is equal to V into P saturation square upon RT. This is how we calculate F saturation. जो उसमें दिया है हम नीचे F saturation ऐसे कैलकुलेट करेंगे because you know vapor pressure, we can calculate this F saturation, and once we know F saturation and we know P saturation, we can calculate F fugacity.
सर वो हमने नीचे बोला था ना एफ एल इक्वल टू एफ सैचुरेशन.
FL equal to F saturation निकाल लिया हमने. FL equal to FV लिया ना. हाँ, यहाँ पर ना, this is for at equilibrium. Yes, this is the condition that F saturation is equal to FL, not FV.
यस सर, तो उसकी वैल्यू 0 हो जाएगी ऐसा.
इसकी 0 हो जाएगी वैल्यू.
एफ इक्वल टू एफ एल डाला ln1 एफ एल इक्वल टू एफ सैचुरेशन डाला तो इक्वेशन में.
यहाँ पर
हाँ सर.
बराबर है ना, but because at that pressure P is equal to also P sat ना. So this is not at F sat ना. This is not at F sat. This is at any pressure. If I want to calculate the fugacity at any pressure, not at saturation pressure, this is how what equation I'll use. Saturation pressure में 0 हो जाएगा because right hand side is also 0, right? P is equal to P sat हो जाएगा. But if I want to calculate fugacity at any pressure, need not be saturation pressure, then I'll use this equation.
ओके सर,
समझा ना. सैचुरेशन प्रेशर तो एनीवे राइट हैंड साइड भी 0 है ना, बिकॉज P इज इक्वल टू P सेट हो जाएगा, तो राइट हैंड साइड भी 0 हो जाएगा ना. बट इफ आई वांट टू कैलकुलेट प्रेशर fugacity at any pressure other than saturation pressure, then I can use this equation.
यस सर.
ठीक है. Okay. So next we look at activity. We have seen fugacity. Fugacity is more relevant for gases. Now we look at activity because liquids are a little different. Okay. So vapor pressure of non-volatile solids and liquids is very low at normal temperatures, and fugacity determination is not easy, not possible for these. So we define a term called activity instead of fugacity for liquids. And how is it defined? Activity is relative fugacity or fugacity upon fugacity in standard state. So if you take fugacity at actual condition and again fugacity in standard state, that is called activity. This is used for reaction equilibria, homogeneous reaction equilibria. We define A is equal to activity is equal to F, actual fugacity, upon fugacity in standard state, F0. This is the definition of activity. We'll see how it is used. Okay. For gases, standard state fugacity is equal to 1. We have seen that, right? Low pressure pe F0 is equal to P, right? If I take pressure equal to 1, F by P is equal to 1 liya na humne, then it becomes 1, standard state fugacity. And therefore for gases, activity is equal to fugacity because F0 is equal to 1. If I apply this definition of activity to gases, then activity is equal to fugacity for gases only, but not for liquids. ठीक है, समझ में आया एक्टिविटी का डेफिनेशन?
Yes, sir.
Okay. Because we are going to use this term in liquids, right? Okay, so dg is equal to v dp है, is equal to RT dln f, right? At constant temperature लिया था हमने. So change in free energy when a substance goes from one state to another state, you can integrate from G0 to G, from standard state to G, and right hand side is RT ln dln f, from standard state F0 to F. What you get is delta G is equal to G minus G0, RT ln f by F0, and that is nothing but RT ln A, because we defined activity as F by F0, fugacity in actual condition divided by fugacity in standard state. So that is RT ln A. ठीक है? Equation 1 is okay?
Yes, sir.
Okay. So we have seen this. If we take it, dg is equal to vdp minus sdt रहता ना, और isothermal लिया condition, it becomes dg equal to vdp, and if you go from say standard state p0 to p, integrate, and g0 to g, what you get is delta g equal to g minus g0 v into v अगर constant लिया हमने liquid के लिए बाहर, तो p minus p0. ठीक है? Because we are assuming incompressible. So if you compare equation 1 and 2, delta G equal to RT ln A and delta G equal to V into P minus P0, the left hand side is same, so right hand side has to be equal. So what we'll get is RT ln A is equal to V into P minus P0. ठीक है? And that will give us ln of activity is equal to V upon RT into P minus P0. ठीक है? Is it okay? Any questions on this?
सर वो क्या लिखा है P valid for solids and liquids?
See, when you say V, ये integrate किया हमने यहाँ पर. We have taken V outside integral, right? We can take out V outside integral when V is constant. V constant कब होता है? When it is not changing with pressure, right? Because integral with respect to pressure है ये. What we are saying is incompressible liquids रहता है. Incompressible liquid means when you increase the pressure, the liquid volume doesn't change much. Then only we can take this V outside. और solids में तो change ही नहीं होता volume, because कितना pressure apply कर volume of solid doesn't change. So it is valid for solids and liquids. We can take this V outside the integral for solids and liquids, and then we can get integral as P minus P0. ठीक है? That's what it means. Because
Yes, sir.
we are saying that V does not change when we change the pressure from P0 to P. There is no change in V. So we can take V outside this integral, and what we get is this integral. ठीक है? और किसी को डाउट है? So let's get back. So this is what we get. ln of activity is equal to V by RT into P minus P0. So it is useful for solutions in liquids. And कुछ example है. You can see that example later. Let us finish this effect of temperature on activity. Then we see the example. So we know delta G is equal to RT ln A. And if we take this R ln A is equal to G by, if we divide by T, we get G by T minus G0 by T. Again, we are doing the same thing which we did for fugacity and chemical potential, right? यहाँ भी ऐसे किया था because we get a simple form. So differentiate with respect to temperature at constant pressure. What you get is R ln A double ln A by double T at constant pressure is equal to double G by T by double T at constant pressure minus double G0 by T by double T at constant pressure from this equation here. Differentiation. And we know Gibbs-Helmholtz equation is double G by T by double T at constant pressure is equal to minus H by T square. ये derive किया था हमने, right? So we can directly substitute for this in equation 1. And what we'll get is R double ln A by double T at constant pressure is equal to minus H by T square इसके लिए and minus H0 by T square for this term. Minus of minus. What we get is double ln A by double T at constant pressure is equal to minus H0 minus H by RT square. याद आ रहा है कुछ ऐसा देखा था फॉर्म पहले हमने?
Yes, sir.
सिमिलर इक्वेशन देखा था ना हमने पहले, राइट? तो सिमिलर टू fugacity. Fugacity में था double ln F by double T at constant pressure is equal to H0 minus H by RT square. So the form is same because F and A are related. Right? जैसे G और mu और अगर देखा ना, they are all related. So the form of equation is going to be same. Chemical potential के लिए it was minus HI by T square. Form is same only. यहाँ पर सिर्फ R नहीं है because it is mu by T. So what this is, all these equations जितना भी derive किया, the derivation almost similar है और answer भी almost similar है. So this is the effect of temperature on activity, similar to what we saw, effect of temperature on fugacity. ठीक है? Any question on this?
No, sir.
Okay, so next let us see effect of pressure. Delta is equal to RT ln A is equal to VdP है. So differentiate with respect to pressure at constant temperature. What you get is RT double ln A by double P at constant temperature is equal to, यहाँ पर ये इधर आ गया नीचे, and what you get is only V on the right hand side. And if you take RT here, what you get is double ln A by double P at constant temperature is equal to V by RT. Again, कुछ याद आ रहा पहले वाला fugacity में कैसा था? Exactly same. Double ln F by double P at constant temperature is equal to V by RT. ठीक है? केमिकल पोटेंशियल के लिए था double mu I by double P at constant temperature and N is equal to Vi. RT नहीं आया because of mu is equal to RT, उसमें राइट हैंड साइड में RT आता है, इसलिए only Vi bar. But form is almost same. You can say fugacity activity exactly same. Chemical potential थोड़ा different आएगा because of units of fugacity and chemical potential. Fugacity के units क्या है? What are units of fugacity?
Same as pressure.
Pressure.
और chemical potential का joules per mole. So it's different. ये इससे वो different है, इसीलिए you get different equation here. बाकी और कुछ same है, बाकी other same. ठीक है? Any doubts on activity? Before we see that example, let's see the example.
सर यहाँ पे वो केमिकल पोटेंशियल का इक्वेशन क्यों लिखा है?
बताया ना मैंने, केमिकल पोटेंशियल म्यू का यूनिट्स क्या है?
हाँ,
म्यू का यूनिट्स क्या है?
जूल्स पर मोल।
पर मोल।
फिर विस्कोसिटी का यूनिट्स क्या है?
एटमॉस्फेयर या सेम एज प्रेशर।
So units different to the right hand side different है ना, because you want units same units ना, left hand side right hand side units same होना चाहिए ना. यहाँ पर units है pressure, right? So this is V by RT. This is accounting for that. इसलिए अलग आता है ये chemical potential का equation. Whereas viscosity and activity you get same equation, because activity is equal to F by F0 ना.
Yes sir.
So let us see that example which we referred to. I'll come back to that. Example 6.31. Okay, so let's see. Can you see this? Example 6.31.
Yes, sir.
Okay, so determine the activity of solid magnesium. Molecular weight is given at 300 Kelvin and 10 bar. The reference state is 300 Kelvin and 1 bar. So generally pressure 1 bar लेते हैं. The density of magnesium at 300 Kelvin is 1.745 into 10 to the power of 3 kg per cubic meter, and I assume constant over this pressure range. So we can use this equation 6.149 जो हमने derive किया अभी. ln of A is equal to V is, what is V equal to? यहाँ पर what is V? Capital V. What is capital V? What does capital V represent?
The volume.
Molar volume, because we are taken PV equal to RT ना, so it is molar volume. So molar volume कैसे निकालेंगे density से हम?
So molecular weight by density.
Yes. So molecular weight is 24.32 दिया है, density 1.74 10 to the power of 3 होना चाहिए. Okay, and pressure is 10 bar minus standard state is 1 bar, right? 10 minus 1 into 10 to the power of 5. And अच्छा ये conversion के लिए से 10 to the power 6 डाला है, because he is taking 8.314. ये पास्कल में लिया 10 to the power of 5 and 300 Kelvin. So R is 8.314. So conversion की वजह से 10 to the power of 6 हो गया. And what you get is ln of A is equal to 5 into 10 to the power of minus 3. And from which we get activity is equal to 1.00504. Very close to 1, but it is still not 1. थोड़ा different है. We'll see later कैसे define करते हैं activity का standard state वगैरह. But let us take this for time being. So equation ये है, तो हम वो directly we can calculate based on density and pressures. ठीक है? Any doubts, questions on activity before we proceed to the next topic? Okay, so far we considered only pure components. जो हमने देखा था, gases का भी pure component देखा था, liquids का भी pure component देखा. Now let us look at solutions. There's nothing about pure components, right? We have to deal with solutions all throughout in chemical engineering, right? So for pure fluids, we have seen dg is equal to RT, dl and F, and this is how we define the standard set, right? Limit of F by P at low pressure is equal to 1. देवेंद्र याद आ रहा है ये?
Yes, sir.
This is how we define standard set. Because we can't do this, so we define it related to pressure. That means at low pressure, very low pressure, F by P is equal to 1. Okay. So viscosity of component I in solution could be gaseous, liquid or solid. We can write instead of dg it will be d mu I, because for solution we have to write for a component dg or d mu I, chemical potential, is equal to RT, dl and Fi bar. Similar to this one, we write this equation. जैसे हमने पहले किया था ना, किसके लिए किया था हमने? From pressure we derived viscosity, right? किया था कि नहीं? viscosity equation कैसे assume किया था? याद आ रहा है कुछ? अरे आप लोग कुछ जाके पढ़ते हो कि नहीं घर पे? Because if you don't read, thermo is not going to be easy. If you just come here and sit in the class and think आपको याद हो जाएगा या समझ जाएगा, it's not going to be easy. It's not going to work like that. Thermo theory subject में चल जाता है, यहाँ पर नहीं चलता है. You have to go back, guys, because that's why I share the notes with you. You have to go back and read it and understand it. Just sitting in the lecture is not going to help. Point जो concept रहता है वो fix करना पड़ता है दिमाग में. You have to go through it on your own, at your pace, at home, then only it will be fixed. Otherwise it's going to evaporate. It's very volatile. It's like organic chemistry. Okay. So this is for pure fluids. That's why it is molar free energy. And for components in solution, we define d mu I, that is chemical potential. What is chemical potential definition? Who can tell me?
Partial molar Gibbs free energy.
Partial molar Gibbs free energy, right? So it is delta GT by delta Ni at constant temperature, pressure, Nj not equal to I. इतना याद रहना चाहिए आप लोगों को. So we cannot take G here because we're talking about solutions here. G here we're talking about pure fluids. So we replace G with mu I, this Gibbs free energy, this is partial molar Gibbs free energy. And RT, dl and F की जगह पे we are talking about Fi bar, that means viscosity of component I in solution. Similar form, this is for pure fluids, similarly we define for solutions. And again we define standard state for viscosity Fi bar in solution is limit of Fi bar by Pi bar. Pi bar is partial pressure when P tends to 0 is equal to 1, similar to what we have done this for pure fluid. Similarly, we are defining it for solutions, right? So mu I is nothing but chemical potential of I. Fi bar is viscosity of component I in solution, and Pi bar is partial pressure of component I in solution. So that's how we define. See, we always look at defining of viscosity, then viscosity in solution. पहले pure component का define किया, like this we define. Then we define for solution along the same lines. And standard state is also defined along the same lines. Once you understand that for pure components, you can understand for solutions also. ठीक है, कोई डाउट है इस पे, क्वेश्चन है? It's by analogy, right? So you have seen and we define always by analogy, right? You have देखा ना मास ट्रांसफर एनालॉजी देखा है कि मास ट्रांसफर मोमेंटम ट्रांसफर किया है कि नहीं?
Yes, sir.
Momentum transfer, heat transfer, mass transfer, there's a by analogy, right? There are a lot of things. So this is going to behave like this, it's going to behave like similarly like this. Pure component में ऐसा होगा तो solution में भी similar होगा. This component is same. The thing is instead of pure component, it is in solution. ठीक है, any doubts, questions on this? For solution कैसे define किया हमने?
Yes,
ठीक है,
sir.
so carry on from here next time. I'll stop the recording and then we can continue.